Bonjour tout le monde. I will speak English. I will switch since the first speaker will be speaking English. We're a bit early, so it's always worrying to start a conference too early, but maybe we should do that. So the first speaker is Professor Thomas Mühlherr, who is here, and he will be speaking about the Abelian Tits set. I give the floor.
Thank you for the introduction. And before I start, I would like to thank the organizing committee for inviting me to give a talk on this event. The subject of my talk is Abelian Tits sets. And this is joint work with Pauline Jansen from Ghent. And I would like to start with a main result of Tits, which is the classification of irreducible buildings, spherical buildings, which he published in 1974. So it states irreducible spherical buildings of rank at least 3. They are all classified, and one way of stating the classification theorem is to say that they are all of algebraic origin. By this it is meant that it comes from a Bn pair associated to an algebraic simple group over a field, a classical group, or in small characteristics you have also groups of mixed type. And of course you may wonder about the rank 2 case. Well, it was already clear you can construct by free constructions buildings of rank 2, but Tits proposed already in 1974 what is called the Moufang property. Moufang condition. And he suggested that the Moufang condition would be precisely the condition in the rank 2 case that will characterize those buildings of algebraic origin. And this was actually then accomplished, this result, by Tits and Weiss in 2002. So for spherical buildings of rank at least 2, irreducible spherical buildings of rank at least 2, so to speak, there is a clear picture of what is going on, at least for rank at least 3. Moufang is automatic. Rank 2, with the Moufang condition, you characterize those of algebraic origin. And then there is, of course, the rank 1 case. And rank 1 buildings are just sets. But Tits introduced, well, the Moufang condition for sets, and these are called, the corresponding structures are called Moufang sets. He introduced them in 1992 because of, well, they were just convenient to classify, to find a language for the classification of twin buildings, but they were actually known under or other name like abstract rank 1 group or split Bn pair of rank 1. But he also addressed the question to which extent one could say that they are of algebraic origin, and he gave his very last course here at Collège de France was about Moufang sets, and he addressed the question what can be said whether they are of algebraic origin, and also he associated to several known Moufang sets geometries that would help to analyze them. So what is a Moufang sets are just special cases of what we call Tits sets. And they were introduced quite recently by myself and Richard Weiss in 19. And we got interested in these Tits sets because we were interested in geometries that are not defined over fields or with anisotropic structures, but where you allow also isotropic groups as coordinatizing structures. So what is a Tits set? I would like to start with an example. Well, take a finite dimensional vector space over a field. Say its dimension is n+1 and assume it is at least 2. And then what you can look at the set of maximal flags in this vector space. And for each such flag, you define the unipotent group for that flag, which is just the G, the linear transformations, such that you stabilize C and you require that it is unipotent. And then you can form the pair. And this pair, this is a Tits set, just a set where you have for each point a subgroup of the group of permutations of the set. So, and I will call this Tits set. This is a Tits set associated to the building of type AN over the field F. Okay, so what is a formal definition of a Tits set? So we start with a pair consisting of a set X and a family of groups. So this is just a set, and we require that we have at least 3 points in that set. And here we require that for all x, in X, we have a non-trivial subgroup of the symmetric group. And then we form the group generated by all these subgroups. And we introduce an opposition relation on the set of points, just depending on the set of subgroups. And this is the points opposite x for a point x in X. This is just the set of all points in X such that the corresponding groups intersect trivially. And now with this notation, T is a Tits set. If for all x, y in your set and G in G, well, first you require that the group Ux stabilizes X. And is regular on the set of opposite points. So you have this sharply transitive actions on the points opposite X, and you stabilize X. You require that the subgroup, this family of subgroup is normalized, so we require that Ux to G is just Ux to the G. The third condition is that whenever you have 2 points, you find a third point which is opposite both. So X op intersect Y op shouldn't be empty. And the last condition is when 2 points have the same opposite set, they will be equal. So if X op is equal y up, you want that x is equal y. So that is the definition of a Tits set, and you can convince yourself that this is a canonical example of a Tits set. Now, if you have a Tits set, you call it abelian. If the root groups ux are abelian, and you call it a Moufang set if you are always in this case whenever x and y are distinct. Another way of saying is if you have two distinct points, then they are already opposite. So I would like to say something, a remark on Moufang sets. So if you can, this Tits set will be a Moufang set precisely when, so Tn, Tan is a Moufang set if and only if n is equal 1. And in this case, if you have n is equal 1, the set of chambers is just what is known as a projective line. So this is just a set of points f with a point at infinity. And now there is a construction due to Tits and Weiss from 2006, and they show how to associate to a Jordan division algebra a Moufang set with abelian root groups. So if you have J, a Jordan division algebra, then you can define a Moufang set Mj, which will be just the projective line over this Jordan division algebras. And the root groups, they are all isomorphic to the additive group of J. And going back to the original question whether all Moufang sets are of algebraic origin, for abelian Moufang sets, this means precisely that you want to show that each abelian Moufang set is provided by a Jordan division algebra. And this is an open question. So there had been progress made, but it's still an open question and a prominent open question in the field. So I want to give you more examples of Tits sets. These are the Tits sets of index type. So what you do, you start with a delta, a Moufang building of type WS. So spherical building, so this is finite, a finite Coxeter system. And delta will be just, I look at it, we have a set of chambers and a distance function in the Y group. That's one way of defining buildings. And what you can do is you can always form this example right from the beginning. You take all chambers. So this is our chambers at C. And if you define the Moufang property for arbitrary spherical buildings, then it's part of the definition that you have these groups you see. And this will be a Tits set. But these are maybe not the Tits sets we are heading for. So I would like to generalize this a little bit. If you take a subset of S, which is not empty, and you require that it is invariant under conjugation with the longest, this is the longest element in our finite Coxeter system. Then what you can do, you can define Ti of delta. This will be as a set. You have delta I. So these are just the simplices of type I. And then you can define the root groups for an I simplex. The group U alpha will be just the intersection. You take all chambers containing A and you take the intersection over the groups that you already have. So there is a canonical way whenever you see a subset of S that is invariant under conjugation, you get a new Tits set for free. Maybe I want to show you one example. Of such a Tits set of index type. We take a 2k dimensional vector space, and as X, we take all the subspaces of V such that the dimension of V is k. And if you have for such a subspace, by choosing a suitable basis, you can identify the root groups associated to W. That will be just a matrix where I have here the unity matrix, here the unity matrix, here A, and A you can choose freely in the ring of K times K matrices over F. So these will be the root groups, and you see the root groups have already a structure of an algebra in this case. And this is what you can observe about Tits sets, Abelian Tits sets of index type. So here is a fact. We start with an irreducible Moufang building of rank at least 2. And we assume that we have a Tits set of index type associated with delta for some I. And we assume this to be abelian. Then what you can say, well, this is just, we know all these spherical Moufang buildings of rank at least 2 due to the result of Tits and Weiss. So we can go through the list and check which one of these are abelian. And what you see is that the set I has always cardinality 1, and you have basically 8 cases. So the first case is a case that we already have seen. So this is the building will be a 2k minus 1 over a division ring, and I will be just, if you draw the diagram, this is a vertex k. So this is the index of this abelian tit set. Then you have some other cases. Bn so VQF is just a quadratic space over F. And in this case, you have in the Tits-Weiss notation, you have a building of type Bn. And in this case, I will be just this vertex. You have Cn. And there the parameter system is a so-called involutory set. And you have this case. And another case is E7 over a field F. This will be just this case. And as I said, there are 8 cases, but these are, so to speak, the generic cases are the most interesting ones. The others are more like specialized. But what you can also see, you can just make this list, but what you can also see, in all cases, moreover, there exists a natural Jordan multiplication. On the root groups. And these yielding simple Artinian Jordan algebras that are not division. And all these algebras, the simple Artinian Jordan algebras that are not division, they are known by work of Jacobson. In the 1960s. And then you observe that if you do this list and you do these exercises, that you get all of them. So you get all simple algebras, simple Artinian non-division algebras just by this list. Just by comparing it with Jacobson's classification. Now, this is not surprising because this fact is already stated in a paper of Borel and Tits in 1973 for algebraic groups. So this observation, they already mentioned it 50 years ago, but now in the context of buildings you get some other exotic Jordan algebras, but you have this bijective correspondence. Okay, so what would be the Jordan algebras that you get out from in this list? So this is the example that we have already seen. So this is the Jordan algebra. You just have an associative algebra and you can make it to a Jordan algebra. Here you get the Jordan algebras which are called of Clifford type. And here you get the Hermitian ones. And here you get the Albert algebra. And that's basically what says Jacobson's classification, that you have three types: Clifford, Hermitian, and the exceptional Jordan algebra. Okay, so I want to come to the problem of, or to looking at abelian tit sets. So, well, I want to talk about geometry. So the idea is, if we start with a tit set, we want to associate a geometry to such a tit set. So let's T equals xy be a tit set. And, well, we want to produce suitable subsets of X and an incident structure on them. And one fruitful approach is to define, whenever I have two distinct points, I can define what we call the hyperline generated by X and Y. This is just, by definition, all points in our set such that the root group is contained in the group generated by the root groups of Ux and Uy. So this is just a natural definition, and we call all these subsets that we get in this way, we call them hyperlines. So this is the hyperline through X and Y. Now, why is this a sensible thing to look at? If you assume that, that our tit set is of index type, then what you observe is that whenever you form a hyperline, you get a subset which Tits calls a shadow of a simplex. So this is an I shadow of a simplex for some simplex A in delta. So these hyperlines are shadows of certain simplices. You don't get all the shadows, but you get a subset of the shadows. And in fact, Tits introduced the notion of a shadow space for a building. So that is also in his book, in his lecture notes in '74. So you can form the shadow space of a building, and this is what is called a line space. The points of the line space are just the I simplices, the simplices of type I, and then the lines of this shadow space are the minimal hyperlines. The minimal I shadows. That are not reduced to a point. So if we want to produce our line space or our geometry just from an abstract tit set, and we want to see a building, we need lines, and therefore we consider Artinian tit sets. So T is called Artinian. If the set of all hyperlines satisfies the descending chain condition. So that's something that we need to start to get a geometry. Yeah. Some terminology for line spaces. So if you have a line space, so what is a line space? It's just a pair. So this is a set of points. And this is a set of lines. And these are just subsets of P, and you require that they contain at least 2 points. And whenever you have such a structure, a line space, what you can define is you call P and Q 2 points in your space. They are connected or called collinear if there is a line containing both. And once you have defined collinearity, you can form the collinearity graph. And you can, there is a natural distance on the set of points, which might be infinite. It's just a graph theoretic notion. Did I? So I call them, sorry, thanks. I call them collinear if the 2 points, if I find a line containing these 2 points. The vertices are the points, and they lie on an edge if they are collinear. Okay, so we have when we have a line space, we have a natural notion of a distance, which might be infinite for the points, and this is actually important. For the statement of our main result. So the theorem, the main result. We take T to be a tit set, Artinian and Abelian. And we form the line space XL, and these are now the minimal hyperlines. And then we can conclude that this space is connected. And actually has finite diameter. I will call it n. And so that's the first statement. And the second statement is, whenever you have 2 points at maximal distance, and if you have a hyperline containing one of these 2 points, then the projection onto H of x exists. And by this, it is meant that I have a point P in H such that for all other points in H, there is a minimal path going to Z passing through P. So and this is a most important property for buildings. In buildings, you see all these projection mappings, and in this particular graphs or line spaces, you see, so to speak, a shadow of these properties of buildings. And what we do with this result, we just take this as a main axiom for a point line space to be a Jordan space. And in the next step, we analyze the structure of Jordan spaces, and they have a very nice structure. Which is the following proposition. Let sigma be a Jordan space. The first part is a decomposition theorem, so you can decompose it uniquely where the sigma I are irreducible Jordan spaces. So each Jordan space has a unique decomposition into irreducible ones. And the second statement is, if you have a Jordan space, so if sigma is irreducible and the diameter is at least 2, then this sigma will be a shadow space in the sense of Tits, and the delta and I are in the list. Or it will be what is called a polar space of infinite rank. So we know all these spaces just by doing geometry. And then we can get a corollary out of this, especially from part B. Namely, we can go back to Tits sets. So let T be an Artinian Abelian irreducible in the sense that its Jordan space is irreducible and not Moufang. So we call these tit sets that are not Moufang isotropic. Then the conclusion is then this tit set will be isomorphic to some tit set of index type where delta I are in the list. Or it is a tit set to some quadratic space with infinite bit index. But for all of those, we have Jordan algebras. We have simple Artinian Jordan algebras, and all of these are not division. So the consequence of this corollary is that if you look at the isomorphism types or isomorphism classes of tit sets, satisfying star, where star are these four conditions, then you get a one-to-one correspondence to the isotopy classes of simple Artinian Jordan algebras that are not division. So in this case, we have the result that one really would like to have for Moufang sets. But in the isotropic case, we are able to construct these geometries, and then by using the classification of spherical buildings, also in the rank 2 case, so due to Tits and Weiss, we actually can establish, so to speak, the conclusion that one would like to have for Moufang sets just for the case of simple Jordan algebras. That is all that I wanted to tell you.